Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, welcome back to our presentation, our discussion. Today, my friend and I want to present about discussion 2, which is application of integration, with parts by parts. So get ready and let's get started. So, these our group members. We have Nur Ain Nabilah 08 DU 24F1023, Nur Azlina 08 DEU 24F 1014, and me Irfan Naufal 08 DEU 24F 1015, and Mifzal Zafri 08 DEU 24F 1047.
Hi, my name is Mirza Zafri bin Muhammad Fairuz. My number matric 08DU 24 F1047. For this discussion, I will explain the introduction of integration. For integration, we have 5 parts: basic integration, substitution method, integration by parts, partial fraction, and application of integration. For basic of integration, we have poly, log, exponent, and trigo. For calculation, we have 2 parts: indefinite and definite. Indefinite is no limit, and the calculation must have plus c. Definite with limit and have a value, and the upper minus to lower. For substitution method, the equation of the first step is the equation in the bracket become u. We differentiate, and second step is differentiate u respect to x. Du over dx equals to 2. Step 3, find the suitable du. Make dx in front. Dx equals to du over 2. And step 4, change the integration in terms of u. For integration by parts, we have a ranking to choose who can be differentiated as u. The first ranking is log, second poly, third exponent, and fourth trigo. This integration by parts, the calculation have more round, depend on the question given. The formula is uv minus u du. For calculation of integration by parts, the first step is choose the first ranking to be differentiated. If poly is an exponent, we can choose poly over exponent because poly is higher rank than exponent. For step 2, differentiate and du in front. For partial fraction, the first step is factorize. Second, split A and B. Step 3, focusing above parts. And step 4, substitute x into A and B. Step 5, replace value of A and B. And step 6, integrate. If get x power of 1, it will be answer in modulus ln. Next is application of integration. So this is the formula of area and formula of volume. For calculation, first step we expand the equation. Second, integrate and simplify the equation if can. Step 3, substitute the upper and the lower limit.
Good day everyone, I'm Norazina binti Maslan, nombor matrik 08 DEU 24F1014. Today, I will introduce you to an important concept in calculus, which is the application of integration to find area and volume. Integration allows us to calculate accumulated quantities such as the area under curve and the volume of solids. In mathematics and engineering, this concept is especially valuable when dealing with irregular shapes and curved surfaces, where basic geometry does not work effectively. This foundational skill helps us solve real-world problems more accurate and efficient. Now, let's take a closer look at how integration is applied. First, when we use integration to find the area under a curve, we are essentially adding up an infinite number of tiny slices between the graph and the axis. This is especially helpful for irregular shapes or functions that aren't straight lines or basic geometric figures. Second, integration can also be used to calculate the volume of solid. One common method is to rotate a region around an axis. Using what we call the disk or washer method, this technique is widely used in fields like physics and engineering to design symmetrical 3D objects such as a tank, domes, or mechanical parts. Overall, these integration techniques are important because they give us accurate results for area and volume, which are vital in architecture, engineering, manufacturing, and even environmental science. In this session, we will learn how to calculate the area under a curve using integration. When we integrate, we are finding the area between a function and an axis, either the x-axis or the y-axis, over a specific interval. To calculate the area under a curve along the x-axis, where the function is written as y equal fx, we integrate from x equal a to x equal b. The formula used is like below. Similarly, to find the area under a curve along the y-axis, where the function is written as x equal gy, we integrate from y equal c to y equal b using the formula like I wrote there. This method helps us determine the space under curve, especially when the region is in a simple rectangle or triangle. Now let's continue with topic B, calculating the volume of a region generated through 3 sig 0 about the x-axis or y-axis. When calculating the area under a curve using integration, we are actually measuring the region between a function and the x-axis or y-axis. This concept is extended further when we revolve the region around the axis to form a 3D solid. There are two common methods to calculate the volume using the disk method for solid shape and the washer method for hollow solid. First, if the region is rotated around the x-axis, we use the formula like below. Second, if the region is rotated around the y-axis, we use the formula like the picture. Finally, for hollow solid, we apply the washer method, where we subtract the inner radius from the outer radius using the formula. This formula helps us determine the volume of various 3D objects generated by rotating 2D regions. Let's look at some examples to better understand topic A and topic B. On the left, we have topic A, which is about calculating the area under a curve. We use the integral of a function either with respect to x or y to find the area under the graph. Now, on the right, we move on to topic B, which involves volume when we rotate the region under the curve. This method gives us the volume of the solid form by revolving the region 3, 0 around the axis.
Hello everyone, my name is Nurain Nabila binti Abdullah. My number metric is 08DU24F1023. My topic is discussion. The first question is how the chosen application of integration to find area and volume in the topic B can be related in the topic A. First and foremost, in the topic A, we are introduced to the function y equal x squared plus 1, which forms a parabolic curve. Second, the region of interest lies between this curve and the vertical line x equal to 0 in the bracket the y-axis, bounded further by the horizontal lines y equal to 1 and y equal to 3. In the meantime, understanding this bounded area is crucial, as it lays the groundwork for applying calculus methods to calculate both area under the curve and volume of the solid from this region. Subsequently, topic B focused on applying integration to find the area under the curve y equal x squared plus 1 from x equal 0 to x equal 2, which corresponds to the vertical bounds from y equal 1 to y equal 3. There's an example for equation to find the area under the curve. And we should find the volume of the solid generated when this area is revolved 316 degrees above the y-axis. First, we should express x in terms of y. X equals square root y minus 1. Then we should apply the Dix method. There's an example for find the volume of the solid equation. For first mathematical solution, area under the curve y equal to x squared plus 1 from y equal 1 to y equal 3. Step 1. Find limits of x. It given y equal to x squared plus 1 and it will be x squared plus equal to y minus 1 and the last answer will be x equal to square root y minus 1. To find area, integrate with respect to x from y equal to 1 will be x equal to 0. Meanwhile, y equal to 3 will be x equal to square root 2. Step 2, we have to set up the integral. So it will be a equal to integrate upper square root 2, lower 0, in bracket x squared plus 1 dx. Step 3, we have to integrate by the value we get from step 2. So it will be a equal to, in bracket, x cubed divided by 3 plus x upper square root 2 lower 0. So we have to add the value in this integrate what we get. So it will be a equal to, in bracket, square root 2 cube divide 3 plus square root 2 minus, in bracket, 0 cube divide 3 plus 0. The last answer will be a equal to 2.357 units square. For second mathematical solution, volume of solid formed by rotating the region about the y-axis. Step 1. Express x in terms of y. From y equal x squared plus 1, solve for x is x equal square root y minus 1. So the radius of the disc is x equal square root y minus 1. And area of the disc is a equal pi x squared. So the last answer will be pi in bracket y minus 1. For the step 2, we have to set up the volume integrals. It will be v equal pi integrate upper 3 lower 1 in bracket y minus 1 dy. Step 3, we have to integrate from the step 2. It will be v equal pi in bracket y minus 1 square divide 2 upper 3 lower 1. So next is we have to add the value in the y. It will be v minus v equal pi in bracket 3 minus 1 square divide 2 minus in bracket 1 minus 1 square divide 2. So the last answer will be V equal to pi cubic units.
Seterusnya, kita akan pergi kepada conclusion and reference for application of integration about area and volume. For conclusion, integration is a powerful tool for calculating areas and volumes, enable precise solution to complex geometrical problems. Techniques like the dishwasher and shell methods allow for accurate modeling of physical systems in fields such as engineering and physics. As Stewart 2016 highlight, this application depend understanding of calculus and its usefulness in measuring accumulation in various dimensions. For reference, number 1, Stewart J 2016 Calculus Early Transcendentals Cambridge Learning. Number 2, Thomas George B. Thomas Calculus. Number 3, Power Online Maths Notes from Lama University Application of Integrals. And number 4, Anton Howard Bevan in Real Life and Davis Stephen Calculus Early Transcendentals.
Thank you. That's all from we. Hope you guys enjoy it.